let's talk about acids and bases and where they come into our lives. So often, after that big, nice, rich meal, you get a little bit of acid reflux, all related to the amount of stomach acids that are produced by nutrition and when we consume food. And if we look back in history, we see that there were several people, particularly some of the kings of England, that had gout. Obviously, a extremely painful experience that was related to the buildup of uric acid in joints. And you might see some situations where, when you look at your dorm room sink or your sink at home and gets all blocked up, and well, how do we get rid of this? Well, if you look at the top of the faucet, you might see some crusty material there, which is typically carbonate. And what we could do is we could actually add some acid to this in the form of vinegar, and that would unblock it. And so this sink over here, we could actually use some acid-base chemistry to get rid of that blockage by using something like vinegar, which is an acid, and sodium bicarbonate, like baking soda, which is a base. And so, for those people that are interested in, chopping down trees, this axe, of course, has started to rust, and we could clean that with some acid. And so now I'll just save you some money, because in the summer, some people, they have these nice boats which are completely covered in algae and horrible stuff, and they really want it to look nice and clean. So you go online and you see that you can buy this Boat Bright for $45 here. Well, actually, if you look at the ingredients on it, all it is actually is muriatic acid, and you could go to the hardware store and pay $7 for it, and it would do exactly the same thing. So I'm saving you money. And if we look at acid rain, we have in the Adirondack Mountains. If you go to the Adirondacks, there's large areas where there's quite a lot of decimation of the forests, and this was related to the production of acidic gases such as sulfur dioxide and nitrogen oxides, which were released into the atmosphere, and then they reacted with the water in clouds, and then they would dissolve in water, and they would rain down onto different properties in the form of acid rain. Typically they would start with NOx and would produce nitric acid, or SOx, and they would produce sulfuric acid. And in the Adirondacks there was some severe damage, but not far west in the Finger Lakes region, where all the wine is grown, the vineyards there weren't affected by it. And so, rather remarkably, both of these areas were impacted by acid rain, but the Finger Lakes region wasn't impacted on the land itself. And the reason for this is the bedrock here in the Finger Lakes contained a base, or a carbonate, which was able to neutralize the acid. Pretty impressive. And so, if we look at a biology point of view, there's lots of areas where acid and bases in your stomach are going to produce different reactions to metabolic properties, and of course you can end up with a large number of different ailments because of this. And so when we talk about acid base, typically in the human body needs to maintain the pH, or the acidity within different organisms. And so we typically use the pH scale here, the blood pH scale, and we also know that in order to excrete things, you're going to typically produce urine, which is going to have its own relative pH. And for those horticulturalists, rather amazingly, hydrangeas, if you grow hydrangeas in acidic soil versus growing them in basic soil, their colours are totally different, which is really quite incredible. And so, where do we see acids and bases? Well, often in, if you open your kitchen cupboards now, you'll typically find things like vitamin C or vinegar. These are all acids. And then you would also find some, rather sketchy drain cleaner, some baking soda or ammonia. These are all going to be bases. And if you went out into the garden, or you went into other areas of the house, you could find a whole variety of different acids and bases. And so what we need to think about is, from a chemistry point of view, we have different definitions of acids and bases. And so the first definition that we talk about is the Arrhenius definition. And the Arrhenius definition basically says that an acid is a compound that donates a hydrogen ion in water, which is a great definition. And then the Arrhenius base is something that donates a hydroxide ion in water. So we're going to produce an H plus ion in water as an acid, and we're going to produce an OH minus or hydroxide in water, which is fabulous. So that's a great definition. The only problem with the Arrhenius definition is that when there are some exceptions, and one of those exceptions that we see are NH3, ammonia, and we know that ammonia is a base, it acts as a base. However, if you look at NH3, there's no oxygen available for NH3 when it dissolves in water to actually donate a hydroxide ion, because there's no O in the base. So as a definition, it's a great definition, but it doesn't really cover everything. And so the second definition that we talk about is what are called Bronsted-Lowry acids and Bronsted-Lowry bases. And these ones basically very similar, but what it's saying is a Bronsted-Lowry acid is a compound that donates a proton to another compound. And it's all about the proton. So a compound that accepts a proton is called a Bronsted-Lowry base. So we're talking about H plus ions. Often when we're in water, we're actually talking about the hydronium ion, which is H3O plus. And so I'm going to come back to Bronsted-Lowry acids. I'm going to just briefly talk about a third definition. We also have the Lewis definition. And the Lewis definition of an acid is something that accepts an electron pair. And so it accepts an electron pair, so it's called an electron acceptor as well. And so in biology we often talk about electron acceptors. So in metabolism we talk about electron acceptors. We also talk about electron donors. And electron donors is the Lewis definition of a base, which means that it donates an electron pair. And the Lewis definition explains pretty much everything. It explains all traditional acids and bases, plus a whole host of different coordination compounds. It's widely used in organic chemistry and is a fabulous definition. And so when we talk about acids and bases, we have these three definitions. And most of the time we will talk about Bronsted-Lowry acids and bases. And so here are some examples of Bronsted-Lowry acids and bases. So a Bronsted-Lowry acid is something that donates a proton, and a Bronsted-Lowry base is something that accepts a proton. So if we look at an acid, so here for example HF, hydrofluoric acid, when you put it in water, often it's going to donate a proton. So here it is, here it donates a proton, and then what's left over is the ion, in this case F minus, the fluoride ion. Now rather interestingly, this fluoride ion F minus has the ability to actually accept this proton and go back and form an acid. So F minus can also act as something that can accept a proton and go back the other way. And because of that, a compound that accepts a proton is called a Bronsted-Lowry base. So F minus actually can also act as a base because it can accept this proton and go back and produce an acid because it can accept a proton. And because of that, F minus is called the conjugate base of this acid. And the only difference between this acid and the conjugate base is actually a hydrogen, because this hydrogen or this proton was donated. And so rather interestingly, when you look at these molecules and compounds, you'll see that there are lots of different areas where you can have acids and what are called conjugate bases. So for example, here's sulfuric acid, and sulfuric acid will donate a proton, therefore it's an acid, and it produces an ion. Now interestingly enough, this ion over here is also a conjugate base, Cb, conjugate base, because this ion here can accept this hydrogen and go back and form sulfuric acid, because a compound that accepts a proton is a base, and so this compound, this ion here, would be the conjugate base of sulfuric acid. And so this goes on and on. So you could have organic acids. So here, this is acetic acid or ethanoic acid. By definition, it donates a proton, therefore it's an acid, and then it produces the acetate ion or the in solution. Well, rather interestingly, yet again, this acetate ion can react and accept a proton and produce acetic acid. Because this can accept a proton, it's what's called a conjugate base. It's a base because it accepts a proton. And then, amazingly, water itself, water can actually break apart into H plus and OH minus. And you know what's a little weird about this is that water can produce an H plus, a compound that donates a proton, so therefore water is acting as an acid. And then, rather interestingly, water is also producing an OH minus. And so, by our previous definition, that said that it could be acting as a base. So actually, water can act as a base and an acid. And if you look at this OH minus here, this is the conjugate base because this OH minus can accept a hydrogen and produce water. So this is the conjugate base. The difference between the acid, in this case water, and the conjugate base, again, is just a hydrogen or proton. And so you can also have acids that are made up of anions as well. Here's HS minus. And HS minus can donate a proton, so it acts as an acid, and it produces the sulfide ion. This again is a conjugate base because it can accept this hydrogen and go back and produce HS minus. And here bicarbonate can donate a proton, so this will act as an acid, and it will produce the carbonate ion, and the carbonate ion can react with the hydrogen, H plus, and it can produce the bicarbonate ion by going the opposite way. So this is a conjugate base because, by definition again, a base is a compound that accepts a proton, and so carbonate can act as a base. And the last one is we could also have cations. So here, for example, is ammonium ion. Ammonium ion can donate an H plus ion, so it's acting as as an acid, donating a proton, and then it produces NH3 ammonia. And ammonia is, of course, a conjugate base because it can react and accept a proton to produce NH4 plus. So this is acting as a base. And so we have these acid-base pairs which are called conjugate acid-base pairs. So this is the acid, this is its conjugate base. And so if we look at H3O plus, the hydronium ion, it can produce H plus, so it's acting as an acid, donating a proton, produces water. And in this particular case, this water molecule here can act as a base. And remember, up here it was acting as an acid. The great thing is water can act as an acid and a base. Here it's the conjugate base. It'll accept a proton and produce H3O plus. So H2O is acting as a base in this particular case as the conjugate base of H3O plus. So of course we also have bases. So a base is going to accept a proton. By definition, anything that accepts a proton is going to act as a base. And this base, once it accepts a proton, it's going to form what's called the conjugate acid, because this acid over here could donate a proton and go back and form this base. So here, for example, hydroxide ion is going to accept a proton because it's a base, and it's going to produce H2O. Now H2O, of course, could act as an acid, and it could donate a proton. Look, it donates this proton and it produces hydroxide ion. So H2O in this case is what's known as the conjugate acid of this base. So we can look at H2O. It itself can go in this opposite reaction. H2O accepts H+. It's accepting, so it's acting as a base, and it produces H3O+. And this H3O+ is the conjugate acid of this base. And so here NH3, which works rather nicely now because this NH3 can accept a proton and it produces NH4+. So a great Bronsted-Lowry base, and by definition is a proton acceptor. And so to summarize, we have acids which are proton donors, we have bases which are proton acceptors, and then we also have this conjugate acid base pair. And so when we have conjugate acid base pairs, what we can do is we can look at these as examples and say, well, at this point can we recognize which ones are which? So if you were asked, in nitric acid reacting in presence of water is going to produce the hydronium ion and the nitrate ion. If you were asked, well, which ones are the base, which ones are the acids, which ones are the bases, you would say, well, this is an acid because it's going to donate a proton. So this little hydrogen here is going to be donated, and what it's going to produce is it's actually going to produce a base over here because this nitric acid donated this proton, and what was left was this nitrate ion. Here it is, here's the nitrate ion. And so what we can say is this is the conjugate base of this acid. And so we're going to call it CB because it'll be easier. So if we then looked and said, well, water over here, water is accepting a proton because water is accepting a proton, and because it's accepting a proton, it's acting as a base. Because it's acting as a base, it's accepting a proton and it's producing H3O+. And then if we look at this, this H3O+ is actually a conjugate acid of this base, because H3O+ could act as an acid, it could donate its proton and produce the water molecule. So these are what are known as conjugate acid base pairs. Here's acid, and the conjugate base of that acid differs from this acid just by this hydrogen or this proton, and so here's HNO3, here's NO3-. The H+ has been donated because it acted as an acid. And so we could look at the next one and we could say, well, when we look at this reaction here, NH4+ plus water is going to hydronium ion plus NH3. NH4+ is, we need to ask the question, is it donating or is it accepting a proton? Well, here's NH4 and here we have NH3, and so NH4 to NH3, it must have donated a proton. Because it donated a proton, it was acting as an acid, and then we could say, oh, well, it produced its conjugate base. So the acid produces this conjugate base, because this conjugate base over here, NH3, could actually accept a proton, and if it accepted a proton it would produce NH4+. So it could act as a base, and it's also known as a conjugate base. So in this case we could look at water and we would realize that water itself in this reaction is accepting a proton, and when it accepts a proton it's producing H3O+, which is the conjugate acid this base. Because what's happened is H2O has accepted an H plus. By definition, it's acting as a base, and it produces H3O plus, which is the conjugate acid of this particular base. And so these are what we call conjugate acid base pairs.